Buenos días. Sí, no está mal. Good morning. Welcome to the first talk of this day. This will be by Favio Miranda from the Facultad de Ciencias, and he will talk about going backwards suffices, some reflections on proof construction for formal verification. And, well, thank you, Fabio.
Tengo esta otra cosa. So, this thing working? Yeah. So, thanks again for inviting me to this nice workshop. First thing I want to say is that at the end, I don't like the title of this talk because I'm not doing some reflections. Instead, I'm doing a proposal on proof construction for formal verification. But the abstract, if you're the abstract, I like the abstract. So the abstract is okay. Second, I couldn't resist to use the blackboards. It was just impossible to resist to these beautiful blackboards. So I use it to put the rules of the system that we propose, and I talk about it on Monday, to do practical logic in the sense of the logic that is used in proof assistance. So here are the rules, and I'm going to use them later. But let me start with some interesting points of view against what I am talking about. This is from a tutorial on how to write proofs, which is a nice tutorial. And let me read a little bit. So, begin at the end and end at the beginning. This is a really, really terrible thing to do. This might have been even worse than leaving out gaps in the middle. Because if you begin at the end and end at the beginning, you monumentally haven't got where you are trying to go. Here's an example and so on. Let's say that this is a bad proof. This is not even a proof. Okay. Second point of view from a nice book on non-classical propositional logics from Eric Schechter, and it says, working backwards is not a method of proof at all. It is a method of discovery. However, beginners sometimes confuse it with proof, perhaps because it slightly resembles an indirect proof, or because they do not understand the difference between discovery and certification, or because working backwards often succeeds in some lower-level math courses. It does not work in most advanced parts of math. So let me contrast this with, for example, some deep mathematical proofs that are performed with the help of a proof assistant. In particular, I like to mention the Phi-Thomson theorem. Which? The Phi-Thomson theorem in group theory. So that is higher level math. And the proof, there is a proof done. The original proof is 254 pages. Then there are books of 1,000 pages about it. And there is a computer-assisted proof in Coq. And Coq, the way we interact with Coq and we do proofs is backward. It's backward reasoning. So that thing is against this opinion. Yeah? But what is backward reasoning? For example, this is from a book called How to Prove It, a Structured Approach, a nice book, which talks about proof strategies. So, for example, it says, it teaches logic and then some basic mathematics, but first teach how to do proofs. So to prove a goal of the form P implies Q, assume P is true, and then prove Q. And then some kind of diagram. So the givens or the assumptions are some, and the goal that I want to prove is P implies Q, And after using the strategy, so P is now a new assumption, and then I have to prove Q. This is also backward, yeah? This corresponds to the backward reading of this rule here. No? Now, to prove an existential, by the way, here I'm using an example in propositional logic, and only propositional logic, but we have all the same I'm talking about. We can do it with first order logic and also with equality. So to prove an existential, then what is the strategy? Prove P of X, where X is the value you decide. Now, about negation. To prove the negation of P, if possible, please express the goal in some other form and then use some of the other proof strategies. By the way, the proof strategy is to read backwards those rules. And to prove not P, so assume P is true and try to reach a contradiction. Here is another book, A Logical Introduction to Proof, with some other strategies about, this time about disjunction. So, talking about diagrams, yeah? Given a diagram containing the form assume P or Q, prove R, there are three ways. So, prove by cases, which is essentially this rule, or a rule which is from classical logic that is not there, so which is the rule that we use all the time in mathematics. Yeah? So if you are assuming or you can prove the negation of P, then you can deduce Q, and with Q, prove R. And the other is analogous. Yeah? But as you see, these all are just heuristic rules, not formal. They are talking about diagrams. This is the last one, I think. So if you give a diagram containing to prove this universal quantifier, then replace this diagram with let X be arbitrary and prove P of X. So if X is already being used, use another letter. Okay. So, but I think this is the only reflection I'm going to do now. What is the relevancy of proofs? As I am talking about proof assistance, it results that proving theorems, proving mathematical theorems is exactly the same as doing formal verification. There is no difference. It's the same software, these are the same mechanisms, there is just no difference. So the value of proof is that it warrants the truth of the theorem. Yeah? But there is a big difference between mathematics and computer science. I should have had here some point of view in philosophy, but I didn't dare to do it. So in mathematics, proofs and not only theorems are relevant. Yeah? We have new proofs of a known theorem, and these new proofs provide new insights into the theory. There are several examples. So, and in formal verification, we're really not interested in the proof. Well, there are some cases that we are interested in particular proof, but at the end, in those cases, I think we are doing mathematics, more deep mathematics. Why? Proofs are irrelevant. Once a proof succeeds, we dispose of it. We are only interested in the verified property. I mean, the process of proving it is not important at the end. Then again, in mathematics, these proof strategies are only heuristics related to backward reasoning, like the ones I presented from those books. But only forward proof is valid, as the first slide says. So once you apply these heuristic rules and you got a proof, then write the proof in a forward way, which is the only valid way. which is the only real proof. So if I am saying that formal verification disposes of the proof, then why to do this last task? So the backward proof suffices. The backward proof is the way we do the proofs in the proof assistant. Then why bother to construct the forward? So mind the gap. The formal proof construction is a process related to backward heuristics and human creativity. I always say, I can teach you some rules of the logic, or I can teach you the syntax of the programming language, or some methodology of the programming language, but I'm not able, I won't never be able to teach you to programming. It's the same as cooking. I can give you the recipes, but I cannot teach you how to cook. I mean, I know the recipe for doing Mexican rice, red rice, and it's terrible. I cannot do it. Every time I try to do it, it's a mess. It's a big mess. Then, from the point of view of purely formal logic, in particular deductive systems, these deductive systems are supposed to help improve formalization. And, well, they really don't help. No? But the mathematicians out there don't do formal proofs in deductive systems, never. The proof assistants are sophisticated implementations of deductive systems at their core. So here's the gap. There is no explicit connection between the formal deductive systems from mathematical logic, from computational logic, and their operational implementation in proof assistants. The connection is given by those heuristic rules, yeah? But they are not formal. So this gap is an important problem in the teaching of computational logic and formal verification. There are no relations. I can teach the deductive system like this in a course of computational logic, then I'm going to a course in formal verification, and then they don't really see the formal relation between those. So like I say, so we teach these kind of systems, and we say that we need to use logic to do formal specifications, and then we have this proof assistant, which is of course, some more sophisticated logic implemented, but the way of programming in the assistant is doing logic in some sense, but it's not the logic that I teach, formal logic. Well, it is. That's what I'm going to conclude now. But it is if I present it in the other way. Now, this is a very interesting thing. At the beginning, I put some slides from mathematicians saying backward proof is not really a proof, it's just a heuristic. So what I'm telling you about now is I'm going to present a formal notion of backward proof. This idea is not new. So it appears in Stick-Kanger's work in 1957. Stick-Kanger has important contributions to automated reasoning. There is a very nice paper by Voronkov telling about that. And in one of those papers, this is taken from that paper. This is a definition of what is a quasi-deduction, so it doesn't matter the quasi now. And it's the only place that I have seen this kind of definition. So a proof of a sequence is just something like this. Huh? A proof of sequence S from some sequence class phi is a sequence is a sequence with this condition. So the sequence begins with an occurrence of S. So it sounds weird to mathematicians. So I am beginning with the thing I want to prove. Yeah? And that's the most terrible mistake in this place. I am beginning with the thing that I want to prove. And then each member of the sequence is either an action or a hypothesis, a member of this class, or is directly inferable. And directly inferable means, for example, this here, A or B, is directly inferable from this. This A and B is directly inferable from these two. So it's an application of the rule in a backward way. Directly inferable application of a rule of inference from succeeding members. So the usual proof, the usual definition in logic books is from previous members. Yeah? It's from succeeding members. What is curious is that the definition is there, and then there is the example, but the example is not related to the definition. So the example is this. The rules of inference are applied are specified to the right, the name of the rules. The easiest way to obtain the proof is to start from below with the sequence to be proved. But then there is no relation with the definition. And in fact, all the technical results in this work never use that formal definition. Why? I don't know. Okay, so now I'm going to do an example. I'm going to do an example. Let me tell you quickly about the rules. So these are the rules of the system that I call practical logic. And, well, these are very well-known rules, but almost all of them. But together, they have, it's a new system with these rules together. In particular, that one is a rule that, as I said before, I have never seen in other systems. Okay, the example is elementary, but it still, let me say something interesting. So we have these three premises, and then let's do the proof, yeah? Maybe I can quickly do the proof in the more usual natural deduction style here. Again, I cannot resist to use the blackboard. So it's something like, okay, I assume this, I assume this, I assume this. So I need to prove P implies S, then, okay, the heuristic thing is I assume P, but this is a different kind of assumption. These are given hypotheses. Then I need to use here graphical device that says, okay, this is an assumption, then from all this I have to prove S. So to prove S, then from 1 and 4 I can prove Q or R. This is some modus ponens. Then I'm doing a case analysis on Q or R, which means that at other level here, first let me suppose Q. If I have Q, then from these modus ponens I have R. And if I have R, from these one modus ponens I have S. Yeah? So in the case of Q, I have S. Then the other case, which is the same level of this, but it's separated. Now I suppose R. Then I have immediately S. So in that case, in the case Q, I have S. In the case R, I have S. I have Q or R. Then at the other level, therefore, I have S. And then at this level, I have P implies S. So this is very difficult to mechanize because this is essentially human. I'm using some graphical devices, I am using some boxes, and so on. This is the usual natural deduction, flag style or Fitch style. So now I'm doing the same, but in the sequence style. So the first step is already terrible from the point of view of intuition. Because here, I start with the given hypothesis. And here I start with something that, okay, why it occurred to me that start this way? Huh? No, that's human creativity. Then I have this, which corresponds to 1 here. I do the modus ponens or implication elimination. Now another, I suppose this Q, which is like this, this here, this 6 correspond to this. Then I have Q or R, which is these 2 here. Then the modus ponens, I have R, well, in the same way. Well, I finally have from P to S, which corresponds to the steps from 4 to 10 to 11. And then I finish. Of course, this proof is more obscure than this. In particular, it has a terrible defect. Those steps, which are 6 steps, so more than the half of the steps of the proof, are using, because there is no other way, are using this horrible rule, because that's the only way, which is saying, okay, the proof, if you assume A, then you have a proof of A. This is again the terrible mistake we do in the first semester in mathematics. Okay, proof A. Okay, I'm using A. Yeah? Of course, I can read another way that this relation is, okay, the proof of this depend on these assumptions. But anyway. Yeah? Yeah, of course. Yeah, the ones that are bothering me are the ones that correspond to these assumptions, not the general hypothesis. But anyway, let me now use the system that I presented on Monday, which are these rules. So I start again with this kind of human creativity out of nowhere. So I pulled this rabbit out of the hat. Then I use the left rule of implication, which is the rule that I say we are proposing, saying, okay, I have Q, but one of the assumptions is Q implies R, then I have R. And then something, again, mysterious. Okay, here you conclude R, and then again, but with some different context. Then, again, this terrible rule. Then I realize that, okay, you have these two because one is with Q and one is with R. Then with Q or R, you have R. Then you have P, but you have P implies Q or R. Then you have Q or R because you have R here. Then you need to use the Coot rule. The Coot rule is the one that is here. And it doesn't appear here. It doesn't appear in the previous proof, but here I need it. So the good rule to prove B, then you can use lemma A. So prove the lemma, and then using the lemma, prove this B that you wanted to prove. Then I do that. The lemma here is Q or R, and I want to prove R. Then to prove this, so then I have R, and I have R implies S, and I have S, and then, okay, I have a P, and I prove S, and I have P implies S. So it's even darker, yeah? But now let me put this. Now we have this horrible rule. I want to get rid of that rule, but I am not able to do it. Only in 3 steps, and they are never this hypothesis, the original hypothesis, never. There are only new ones, which of course correspond to this, this, and this. Sorry, this and this. Yeah? But okay, and that always happens. But okay, yeah, the proof is not easier, yeah? So the system that I talked about the other day, well, it's not really very nice. And let me tell you, the proofs are not so difficult because this rule, the usual rules for conditional on the left, need 2 premises. And they are, the proofs are not so short. But, okay. Now, let's read the proof backwards, yeah? It's the same proof, but I highlighted something. So with the Kanger, the formal definition, if you want. So I need to prove P imply S. Then the strategy says, okay, assume P and then prove S. So I move from 9 to 8. And okay, how I'm going to prove S? I have this previous theorem. Okay, then I need only to prove R. So how I'm going to prove R? And here is the part of human creativity. I don't want to get rid of that. So I need to prove R, then I realize after some time that this lemma, Q or R, is going to help. So I prove the lemma in step 6, and in step 5, I prove the previous goal using the lemma. Now, to prove the lemma, I use this rule here. I need to prove, and I use this previous theorem. So to prove Q or R, I only need to prove P, but this is immediate, yeah, because P is one of the hypotheses. But it was from here. But now this rule appears in a very natural way. Now it appears as, okay, I already had P, and after some reasoning, it results that I need to prove some of the things that I already know. Yeah? It's not like I started with this out of nowhere. Yeah? Now I finish with this. This settles this. Then I prove this using this lemma. And to prove this using this lemma, I'm going to do a case analysis on this, which is this rule. So I'm going to prove R using Q and R separately, which are these 2. This, again, is obvious, because I want to prove R using R. But you see now this thing appear in a natural way. And then Q using R, but to do this, I use this previous theorem. Then I have, it suffices to show Q, but I know Q, and the proof is over. Yeah? But it's the same proof. Now tell me, and be completely sincere. Now it is more clear, the proof now. I'm going backwards. Okay, now the technical things. So the idea is very simple. I have an inference rule, and if I read it backwards, it says, so to prove this, it suffices to prove this premise. Yeah. To prove this conclusion, it suffices to prove this premise. So this thing, this informal thing, this heuristical thing is formalized in a transition. So read this triangle, good. It suffices to show. To prove this, it suffices to show all this. And then the rules become transition rules. This idea is not new. These such transition rules is called a tactic. It's in Edinburgh LCF. And then I have some transition rules. For example, one rule for any one of these, one transition rule for any one of these inference rules. Then I can do with this rule in a kind of mechanical way the backward proof. So let me do some examples, yeah? So to prove A or B, it suffices to prove A, that corresponds to this one. In the constructive way, in the classical way. So to prove A or B, then assume not A and then prove B. To prove A implies B, suppose A and prove B. Or maybe do the contrapositive. Yeah? To prove A implies B, assume not B and then prove not A. Proof by contradiction, which is that rule here. So you want to prove B, then assume on the contrary not B, and arrive to a contradiction. But the contradiction has to be explicit. So find some A such that from not B, and the other ones, of course, gamma, you prove A, and then you prove not A. This semicolon is least concatenation, because these are sequences. Some proof by dichotomy. To prove B, okay, you can prove B assuming A, and you can prove B assuming not A. Yeah? Or, as I said, here's an example with equality. To prove S equals T, then find an R, and then prove S equals R, and then R equals T. Okay. These rules are essentially different from these ones, because this one correspond to rules that have the formula property in some sense. And then these rules can be completely automated. We can automatize completely these rules. But this no. Because here we have to guess. Here we only have these, and then we have to guess which A. So here, for example, we have only these, then we have to guess which R. The good rule, there is another point, because this transition, this backward reading is operational, yeah? So any rule that has two or more premises generates different tactics, different operationally. Because here the strategy is, okay, wrong. Wrong, yeah? So this corresponds to this. This should be, this B should disappear. No, this B should disappear and this has to be B. So to prove B from gamma, forget this, to prove B from gamma, then use some lemma A. So first prove the lemma A and then use it to prove the original B. Or first use it to prove the original B and then prove the lemma. And there are different things in mathematics at the end. Because in one problem, we have the conjecture that, oh, this lemma is useful. Then I use the lemma first, A. Then I prove the original theorem, B. And then I prove the lemma. Or the other way around. Then I say, okay, then first I'm going to prove the lemma. I'm not so sure that that is true. I'm proving the lemma first, and then I use it. So, as I say in the previous ones and this one, the automation is difficult. That's why this is called interactive proof search. Interactive means, okay, I, human, say which A, which one is the lemma, or which one is the term that I'm going to put in the middle to do a proof by means of transitivity of equality. Or I am saying which B is the one that is producing the contradiction in a proof by contradiction. Okay. So if these rules have are transition rules, then I can define a transition system. So where the set of states is just a finite sequence of goals. A goal is a sequence, the whole sequence, not just the formula to the right of the turnstile, the whole sequence. The initial states are sequences of length 1, or just one sequence. There is a final state, which is the empty sequence, which says, okay, I don't have anything left to prove. Yeah? So, and the transition relation is given by any basic rule for any inference rule, and then this rule that says, okay, if you can add some pending goals, and then if you prove the first one, and you do a transition step in the first one, then you can put the pending goals in the step. So let me see again some of these tactics. I have here some new device, which is useful. So we use labels for the hypothesis. So this here is only saying, okay, H is a proof of A, or denotes the assumed proof of A. Yeah? So for example, the transition corresponding to this one, okay, to prove A or B, first prove A and then prove B. A or B, well, it suffices to prove A. Prove A or B, assume not A, call this assumption H, then prove B. And this one corresponds to this. Okay, to prove B, and you know that H is the term A implies B, then prove A. And these are called instruction, correspond to these two up here. To prove C using A and B, then it's enough to prove C using A and using B separately, and so on. This corresponds to could. This corresponds to could. And, okay. Now, there are some ones in red. Okay, later I'm telling that. Now, I didn't see the title. Okay, yeah, we have this heuristic process to do proofs, and the rules correspond to three different strategies. So the first one is I analyze the conclusion. I see the logical form of what I want to prove, and then I use some of the corresponding rules, yeah? Right rules or introduction rules. The other is I analyze a premise, and according to the form of the premise, I do something. This is the defect of the natural deduction system in sequence style, of the original one, because the left rules, which are called elimination rules, are not, we don't see a particular premise. So, for example, that one. Could is the same as modus ponens. Because The only difference is that I changed this by this. Yeah? But see that if I put this one, I don't see anything on the left. Yeah? Here I'm saying the A. That's why natural deduction using sequence is terribly bad. That's why the first proof that I say, okay, I have 6 steps which are the use of this, that are using this horrible rule. That's why I need them. That's why this is more practical. Yeah? And the third heuristic is lemma assertion. So I guess a lemma, I realize that this lemma is going to help me, then I use it. And then, as you see, and we're going to see in the example, same example as before, it has to be some way of discarding proofs, goals. And here are some ways. The first one comes from this horrible rule, but now it's very nice. So if what I want to prove is A, but I'm seeing that I already know A, then it's gone. I don't have nothing left to prove. Yeah? Or this one. If I want to prove A of t, but I know that for all xa, then I'm done. Yeah? Or this, which is classical. Well, not classical, really, it's intuitionistic. But which involves contradiction. So if I want to prove B, but I know contradictory information, which is HA or H1 not A, then I'm done. Or reflexivity. I want to prove T equals T. Okay, I'm done. So now the same example, this style. I need to prove P implies S. So I introduce P, call it H4. I apply H3, and you see why I add the labels. Yeah, can't name it. H3 is R implies S. So to prove S is enough to prove R. Here comes the creativity. I need the lemma. Here are 2 goals in the same step, yeah? Separated by this semicolon. First prove the lemma, and then prove R using the lemma. Yeah? So I'm now focusing on the first, because this is a sequence, there's an order. I mean, the order is not important. I can say, okay, first this, but always the same order. Because of the operational mechanisms, because of the actual implementations. So now it's applied H1. This is the same. So to prove Q or R, we know H1 is enough to prove P. This is trivial to prove. So this is discarded. Now we have only one. Was pending here. Then to prove this, we use case analysis, which is the stroke H5. So we prove R using Q, and then we prove R using R. To prove this, we have H2. This is trivial. And this was already trivial, but was left, and then we're done. Yeah? So, now this is a formal proof in the sense of Kanger. Yeah? Not exactly, but in the sense of Kanger. So now the question you are going to ask me is, so what? And what is the relation with this and with the usual ones? Okay, here is the relationship for this system. If I start with a sequent proof, and then I do a finite number of steps, then I have this equivalence. If in a finite number of steps, I don't have any goal left, I discard all the goals, then it's the same that to have a forward proof. I can do a formal derivation in the usual sense. And the other way around. No? So I don't need to pursue to do 2 if I have 1. The backward proof suffices. This is what formal verification tasks need. Not mathematics, maybe. But also in mathematics, it suffices. And this is what is done in computer-assisted mathematics. Well, one thing. The system is inspired by the fragment corresponding to first-order logic with equality in exactly the way that is implemented in the Coq proof assistant. As a matter of fact, I put here some things in red because the ones in blue are available in Coq, the ones in red not. That's some part that we are working on. So the ones in red are not available. So we have to program some tactics which we can do and fail. But as you see, this is a theorem which is completely independent of the Coq proof system. Yeah? Because it only it's saying, okay, this is a formal way to do backward reading of the rules. So I think, but now will come the discussion, that this is the gap between the usual deductive systems, the usual proofs, and the operational mechanisms of computer-assisted proofs. So, some final remarks. This notion put Ganger's definition at work, and it is not particular to this logic. It's applicable to other logics. We have a working problems which we are doing this with a particular system of constructive S4. But it can also be applied to any formalism defined by inference rules. To do the definition and to define the tactics, not the equivalence. I'm not saying that. Here I forgot the structural rules, but they provide low-level tactics needed in the mechanization of structural proof theory. For example, if I want to mechanize Qt elimination, which is also something we want to do, I need to formalize the usual system of sequence, so that, for example, I need to formalize and to use this rule. Which is the exchange rule, because our contexts are not sets, our contexts are not multisets, our sequences are lists. Or another very important is, in the case of these traditional systems, is weakening, yeah? So, and weakening, if we read weakening backwards, it sounds weird. It says, okay, to prove B from gamma and A, it suffices to prove B from gamma. It sounds completely weird, because I'm disposing of one premise. But in formal methods, for example, in event B, which I also mentioned Monday, in event B, this is presented as basic rule. And in the way, in that reading. And it's also useful. It's dangerous because, okay, then I don't know, A. But it has a practical purpose. I'm getting rid of something that is not working. For example, if this talks about arithmetics and this talks about zebras and unicorns, then, okay, get rid of it. I'm not going to need it in this. Okay. Now, related to teaching, we really think that this way to do it with the transition system allows to learn the basic operational mechanisms of some state-of-the-art tool and provides a smooth migration from pure deductive systems to a practical use of logic. So there are some related words that say, okay, I'm doing some software to teach natural deduction, which are very nice. I'm not saying they are bad. But then, after you teach logic, you teach natural deduction with these tools, and then you move to do formal verifications in more serious ways of that tools that are not really related. The language is different. Here is the same. And final thing, technical thing. So what about goal-oriented proof theory? There is some very deep work of Gavai and Olivetti, which is a nice volume, which is goal-directed proof theory, but they are not thinking in human-oriented systems. Yeah? They are again thinking in just doing some generalization of logical programming. So, for example, what can the theory of transition systems say about deductive systems? Now that I have an equivalence or a relation between traditional deductive system and some transition system of tactics. Well, that's all. Thank you.